Hello, good afternoon. Welcome to the first day of daylight savings time, at least in the US. For whatever reason, we started earlier than everybody else. It's kind of a pain. It is the 9th of March, and it is way too soon. At the point that we have it, we have like, what, maybe 4 months, 3 to 4 months that are standard time. It kind of almost makes daylight savings time pointless, but here we are. So today we are going to continue building our compiler based on Essentials of Compilation, book I've got right here in my hands. We'll be working through it and trying to build the compiler that they define in the book. If this is your first time joining this stream, this book is used in multiple universities in the United States and hopefully around the world, I'm not sure, but to teach compiler construction. When I did compiler construction in my undergrad, it was very different. We used the so-called Dragon book. And because it was an undergrad class, we only did the front end of the compiler. And this is a very different kind of strategy than that. I do appreciate having learned everything about lexing and parsing in that class, but we really didn't learn anything about the middle or the back end of compilers. And I think that's what's great about this strategy. Is that you go from the bottom up, which is interesting too, that this was originally in Racket, because that's sort of the Lisp approach. You build small pieces and then you compose those pieces together into larger things. It's the bottom up approach. This also, I think, the focus on making things be really small changes between different phases lets you focus on getting the functionality of that individual step really focused and easily testable. And the thing about this approach, I think what it reveals too, is that they've formalized and separated what a lot of production grade compilers do implicitly. So what these production compilers will often do is actually have the same intermediate form for multiple phases, and they'll still go through those phases, but they won't create a whole new micro language. But that's what this does, and it really lets you see the differences between the results of each phase as separate concepts, and I hope what you've seen so far in the previous 2 or 3 sessions is that we are going from a very basic language and we're building features on top. So, we started with just simple expressions over integer types, integers and operations over integers. And then we added variables, so let bindings. And this kind of building up to the concrete syntax of the language shows that you can compile something by stripping those features away gradually. And that's the approach that they're trying to do here in chapter 2. We're starting at 2.5 today, although I did notice something that we'll go back and fix real quick that was not correct, and we'll fix that. So let's get started. We are we just finished section 2.4 last time, uniqueify variables. But there is one bit that I need to jump back, and we'll switch over to here. When we define this language, which we're about to use this session, hopefully. And I need to restart Z again. Apologies. If you want to follow along, here's the repo, github.com/SeanCribbs Essentials of Compilation. Okay, hopefully that's the last update, Zed. All right. So in section 2.3.1, the CVAR intermediate language, they had a whole chapter or a whole paragraph talking about what the contents of this C program struct is. But we missed a little bit in there, which was, we defined what the info field is. This is going to be used by a phase that we're going to write today, hopefully. And, oops, you don't need to see my iTunes. That was not helpful. Okay, but we didn't actually have the program body. So I'm going to make this a dict again. And the label is a string, and then we have tail is the type. Okay, let's see if I can get this book to sit flat down here where I can see it. Okay, so this is the only thing that we were missing from that section, is that we had defined the info, which is, in a classical compiler's course, they would call this like annotations on the AST, and that's sort of what they're using this for in each of the intermediate languages. But we didn't have a body for this program, so we just had a list, a list of variables there. Not that useful. Okay. So last time we did this uniqueify pass. And again, what this is doing is it's renaming all variables so that they're guaranteed to be unique. This is also sometimes known as static single assignment. Except that a lot of cases where compilers do static single assignment, they'll number a variable when it's seen and then increment the value for that variable's counter, like the suffix of the variable name, as it goes through the scope. But what we're doing is we just have a global counter, and that is returned from each uniqueify exp recursion. So if we ever have to bind a new variable, we increment that counter and we return it. So that's what lets us get, for example, in here, this let binding is inside. So it gets evaluated first. This is like depth first. So this gets the 1 suffix and this gets 2. Okay, so that's what we did last time. A bit that we skipped, but we actually, I think we're in a fairly good spot on, is that we have this uniqueify test, right? And it was just testing their 2 examples here. One of the things that they do, since this is a book for instructions, they have exercises in the text. One of those exercises is like create 5 programs that exercise interesting parts of the uniqueify pass, and then they have the goal there being, you can, since this doesn't change the output language, you can use the interpreter that we wrote for LVAR and interpret it before the transformation and after the transformation and check that the results are equal. So that is an interesting thing that we could do. I'm not sure if we want to do that right here. But what we were testing there was the actual contents of the transformation. So, okay. However, I think that we're in a good spot. Let me just run Gleam build. Okay. Compiling compiler. Haha. Here run test. Okay. So all of our tests pass so far. All right, so we are going to do the next phase. Now, last time we had written out all the phases that they want us to jump through for this particular chapter. And we did uniquify. And now we're going to do remove complex operands. So we have not yet defined this L-mon-var. And they go into detail about what it means in here. Essentially, it's L-var, but all complex expressions are removed. So if you have a primitive operation, all of its arguments have to be atomic. So they have to be either an integer literal or a variable. So there's kind of a question in my mind about do we make a new one? I think the answer is yes, for simplicity's sake, because that's what we've been doing so far. But there could be an argument to say that you might be able to massage this into that, they call it monadic normal form. That's what that's the mon means. Yeah, monadic normal form. Without changing the intermediate language. I think that for the sake of not introducing any mistakes, I think that we should make a new language. Because otherwise what we're going to have to do, instead of using types here, we would have to look at every single expression in this primitive operation and make sure that this is either int or var of expression. So that's more like a validation or a type check than it being built into the types. And if it's built into the types, then we know we can't construct it wrong. So I think I'm going to go that direction. Thank you, Gleam, for having strong types. So what we'll do is we'll, let's see here. We don't need to build an interpreter yet. So let's just copy these things and we'll make a new file. And this is L-mon-var. Okay. So we're going to modify this, and we're going to make this is the atomic type, and this is int, value is an int, or var, name is a string. So we're basically pulling this up, and this is so there's their atomic. So now the primitive operations can only be ATM. Okay, so this is the L-mon-var language. Again, yep. So primitive operations contain only atomic expressions, and atomic expressions refer to literals or variables. Okay, and clearly we're not using any of that yet, so let's just remove those. Okay, atomic expressions are pure. So in other words, we can't have read as part of this language, which is interesting. Which I don't think that we had in L-var anyway. Oh, we had read. So we actually, no, read is fine. But read is a primitive operation, not an atomic expression. Okay, they say another well-known form for intermediate languages is administrative normal form, or ANF. I have heard of this one. Okay, so the L-mon-var language is not quite an ANF because it allows the right-hand side of a let to be a complex expression. such as another let. The flattening of nested let expressions is instead one of the responsibilities of the explicate control pass. So the explicate control pass, remember last time we made the CVAR language? That's the pass we're hopefully going to get to today that transforms this into CVAR. So, okay, so let's make a new pass module, which is going to be remove complex operands, and we'll put the remove complex operands. Okay. And this is going to have to import Lang's lvar. Import Lang's lmonvar. Because that's its input language and that's its output language. Okay, so what we want to do is we want to make remove complex operands. This should be a function which takes an input, which is an lvar program, right? And output is an lmonvar program. Okay, so yeah, it's just complaining about not being used. Okay, so they say we recommend implementing this pass with two mutually recursive functions, which is RCO atom. We don't know what this does yet to do. And RCO expression. Okay. The idea is to apply RCO atom to sub-expressions that need to be commatomic and apply RCO expression to sub-expressions that do not. Okay, so both functions take an lvar expression as input. So lvar.expression. Expression. And I'm assuming what it outputs should be each of these should output an lmonvar expression, right? Okay. Okay, what do they say? So, okay, so the RCO atom is for expressions that need to become atomic, and RCO expression to sub-expressions that do not. Okay, the RCO expression function returns an expression. Okay, so this is where they differ. That's correct. The RCO atom function returns two things: an atomic expression and an A-list, so an associative list, mapping temporary variables to complex sub-expressions. Okay, I guess we don't... So I'm guessing atomic expression means it needs to be an lmonvar, right? A-list mapping temporary variables to complex sub-expressions. So let's... Oops. Import Gleam dict again. So whenever they say a list means associative list, what we need is a dict. And that's going to be, so string for variable name, complex sub-expressions. I'm guessing that's lvar expression. We'll find out. Okay, so let's I'm going to type in the comments here some stuff from the book. So they say returning the example program with the expression plus 42 negate 10. The sub-expression negate 10 should be processed using the RCO atom function because it is an argument of the plus operator and therefore needs to become atomic. So they're saying look into these expressions. Is this atomic? Yes. It's fine. Don't do anything. This needs to be atomic, but it's not. So in order to make it atomic, you have to turn it into an atomic, which means you're basically going to introduce a let binding. Okay, so they're saying that so when RCO atom is applied to negative 10, that becomes, and we just make a variable name. So here it's like temp.1 maps to temp.1 I'm sorry, that's not right. What is that? Oh, this is, I'm sorry, that's not right. So the return value here is an expression which is var, so this becomes a var temp.1, right? And then the dictionary of temp.1. I'm going to use Elixir syntax here, even though it's not valid. So this would be temp.1 maps to negate 10. So this would be, I guess the idea here is that you can find this expression up above and replace it with this variable. Okay, we'll find out. So here's another example they give, which is, they say take special care of programs such as the following that bind a variable to an atomic expression. You should leave such variable bindings unchanged as shown in the program on the right. Okay, so here's their example. A42. Okay. And then here's another let. BA. B. So what they're saying is that this should be unchanged, and a careless implementation would transform this into temp.1 42, and then let a temp.1. And another let temp.2 a. Right, so we don't want to be introducing too many new expressions to make sure that these things are atomic. What we should be doing is looking at the individual expressions and making sure, like checking, are there variables or integers. Unchanged. So this program should remain unchanged by this. All right. Okay. RCO atom. Okay, so I think what we need to figure out what this is. So let's do we're gonna pass. Remember that LVAR program has its body is a single LVAR expression. So clearly we need to go into RCO expression. And that's going to take input body, right? And then what we want to return is lmonvar program of RCO, right? So that satisfies our top, like our entry point. And these are going to be mutually recursive. Okay, so let's think about this program, and this is the RCO atom step. But let's think about how we get to something that is like has no non-atomic expressions in primitive operations. So if we were going to transform this by hand, it would be we introduce a binding. Let's see. So it's saying let temp.1 Okay, so let's look at this from the top level. So this top level expression, this is a primitive operation plus, and 42. This is atomic, so that doesn't need to change. We need to transform this into I'm starting to see it, I think. We need to transform this into a let binding. Because this is atomic, right? But this is an expression. So the 10 is atomic. That's fine. This somehow feels not exactly right. I don't know what they mean by returning this particular type of thing. Maybe what we should do is try to do it without that. Maybe what we'll do is we'll figure out what the return type of RCO atom is by just implementing RCO expression. The other thing is we're going to have to, have something to generate the names of variables, extra variables. So we may have to do that counter thing like we did in the uniquify transformation. Okay, so if I were to do this by hand, I would say, okay, so we have a plus, and we look at the first argument. The first argument is atomic, so we just convert it. Right? It's an integer literal. And then we go look at this. This is not atomic. So we introduce a let binding, temp.1, and then we put -10 in there. So maybe this is like This is your let binding. And this becomes temp.1, right? I think that's how I would transform it if I were to do it by hand. And I think that's what they mean by this. So this is, I don't really, maybe it's that let me reread this thing about RCO atom. Okay, so they both take LVAR expressions. RCO atom returns two things: an atomic expression and an associative list mapping temporary variables to complex subexpressions. Okay. So I think the best way to go about this is start by, we're going to match on the input, and let's fill out all the patterns. So we know that this needs to, and I'm going to move this up to be in that order. So here we have an integer, and we want this to be an LVAR expression. So we know that this is atomic, so we don't need to do anything to it. We just need to transform it. So that gives us the atomic expression, and then we need, remember this needs to be like so. And the same for a variable. We basically do this, but this is var, right? Okay, so primitive operation. This is where it gets interesting. Again, I think that this is not correct. Maybe what their book says is, oh, okay. So, okay, I think I get it now. This is like, here's what goes in the spot that you just had me remove complex operands from. And here's the let bindings you have to attach in order to use that expression. That's what this is. So I think that these are actually L-monvar expressions, right? Because you don't want to have to go back into this and and that's where the mutual recursion comes in. Like if we get down into this and we go, oh, it's still a complex expression, then we go back into RCO expression. Okay, and I think what we're gonna do, we're gonna change. We're gonna introduce this counter, right? And this is for incrementing the variable names. Okay, so this is going to be, we return that and counter because we didn't need to increment anything. Okay. So, if we have a primitive expression, I think that we need to, come on. We need to fill this out. And I forgot one thing. We need to match that. So lvar okay, and I'm going to have it add missing patterns so that we can okay, this does not introduce a new variable, so we can do right? What's wrong with that? Okay, so that's a read op. Okay. Oops, Elmonvar. I don't know how much the language server has. I was going to say, can we rename this variable to something a little bit less verbose? Like LM and L. Maybe we can do that later. Okay, so if you've got negate, then this expression, what we want for that is we want to be able to return, this is a primitive operation, right? Negate, and then A, right? And we don't have what this is, right? And then we don't know what the counter is. So we need to recurse into that expression and make it atomic. So let's go ahead and break this out. So this is where we're going to say we want E and bindings. And let's call RCO atom. And we're going to pass the expression E and our counter. I'm sorry, this gives us a new counter. So at the end here, we'll return new counter. Now the challenge here is so I think what we need to do is have we need to have something that wraps these up as let bindings. So if we have is empty. If we know that the dictionary is empty, then this is interesting. Hi, Chris. Welcome to the stream. Welcome to the daylight saving time stream. Okay, so there's a problem here in my mind. Yeah, I think we need to make a helper function that says like is atomic. And then if this expression is already atomic, and maybe it returns a result, right? Let me think about that. So we'll say check atomic. And this will take an LVAR expression. And I'm going to comment this out and just put to do in here. And I don't know what it'll be yet. Yeah, hi Isaac, good to see you. Yes, that's why I'm tired. Yeah, I know the feeling. That's why my stream's an hour early, Chris. Usually already streaming at this time on Saturdays though, so even with the change. Okay, so we need a match on this. And if it is atomic, we want to return true, I think. The question, I mean, this is going to be, let's have a return bool. I forgot it's caps true. And then we can do the catch-all pattern. I don't really like this, but we'll figure it out. So when I rename this to is atomic, because if this is let me say into atomic, and let's import Gleam option. So I think this is fine. What we can do here is go I and V, and let's do, this is option. Option of lmonvar dot atomic. I think that makes sense. Or not atomic, ATM. So here what we would do is this is just an int, that's just a string. So we'll do lmonvar dot int lmonvar dot var, and this is option dot sum. Actually, let's make sure to import option none sum type option. Okay. Yeah. Okay. So then we can do them without qualifying, and this would be none. There's a question in my mind about, is that what this is supposed to do? Right? But what we don't want to do is, I mean, I guess we can let's just go with it. What other things are available in this? Let's see, Gleam, standard lib. So you can convert from results, is num is sum, lazy or lazy unwrap. So map, I would expect, that's a pretty common thing. Then for chaining, okay, their unwrap is basically Rust's unwrapper default, which is interesting. Okay. So this will give us right. Okay, so let's do into atomic of E. And then if it's none, we have to do this other business, right? If it's sum ATM, then we just do this. Except we didn't increment the counter, so it remains the same, right? Okay. If it's none, then there's an interesting thing here with I think this has to be an atomic, right? And these are the complex expressions, right? Because that's what we were talking about earlier, like what it's returning here is an atomic expression, which is this variable, and then the bindings you need in order to make that variable useful. So I think that this has to be not expression, but ATM. That has to be an atomic. Which makes more sense because of what we were trying to return here. Okay, so if this is not atomic, then we know we're going to have some bindings, right? And what we're going to need to do is have a reducer sort of pattern over this dictionary. And our input to that will be so we're going to return something here and our new counter. We need to get this up here. So this is going to be let ATM. So this is the and then what we eventually return is a kind of fold over the bindings. So let's look at how to do that. Let's look at the dictionary module. So here's fold. Okay, so the accumulator comes as the first argument, and these are the patterns, or these are the key and the value, and you have to return that. So that's what I would expect. So we're going to do dict fold, and what comes first is the bindings, and our initial is going to be this, right? Right? And then our function, so this is going to take the expression and the variable and the binding. Let's break this out. Let new expression is this new expression. Okay, so we just need to construct let bindings. So variable is going to be a string, right? The binding is going to be an expression. And then we're going to wrap the original expression. That's not so bad. You just kind of like reorder arguments. Okay, so what is this doing? So we're saying that RCO atom needs to return an atomic expression and a set of bindings that support that atomic expression based on the original expression that we gave it, right? Now, what's interesting here is that we maybe don't need this into atomic. We just need to make sure that RCO atom doesn't introduce bindings when it's unnecessary. So I think what I want to do is remove that bit. What did I mess up? No, that matches. Okay. Because if interestingly enough, if the bindings are empty, and we know that this is an atomic expression, then folding over that empty dictionary will just return the default. What did I do wrong? There we go. So like this will be a no-op, essentially, and you'll just get back this. Okay, so this is basically, we need to do this the same for minus and plus. And I think that we can do let right now without doing anything, because that does not require atomic expressions on the right hand side. So I think that what we do is we just self-recurse there. So let's do string. Okay. We just do RCO expression, and this will be binding new counter, and so let's, oops, this is V, B, and E. So we call RCO expression on B and counter. And then we do expression new counter 1. I don't know that I need to. It's probably, and that's on E and counter new counter 1. I think I can shadow. Okay, and then we do almon var let V binding expression, and we return new counter 1 as part of that. So I should have done that earlier. That's, you know, this doesn't require any atomic expressions, so I'm going to actually move this whole block up above the primitive operations, because those are the ones that require atomic expressions, and we have to do this self-recursion with RCO atom. Okay, so now we're going to do the same thing with these. That we did for negate, except it has 2 arguments, so it's going to be a little bit more complicated. But let's see if we can do it. So atomic A, bindings A, counter A. So we need this to be over A and counter. Okay, and then we're going to get an atomic expression for B. Bindings B, counter B. And here we're passing counter A to make sure that we don't, so that we introduce new variables from that counter. So that's just sort of our thing flowing through there to make sure we make unique variables. Okay, so then our new expression is going to be similar to this. So let's just copy all this, and we'll redo it. Okay, so we need to merge these two. And I wonder if we might be able to do something like bindings A and pipe it to dict fold. I think that that's the right way to go. And we're going to start with this is minus, and it takes atomic A and atomic B. And then we pipe that to another dict fold, except we'll put bindings B in here, and we'll take that as and this needs to be counter B. Okay, if you haven't seen this bit before, in pipe expressions, it lets you specify the spot that the input comes in with an underscore. So what I'm doing is I'm wrapping the things for A first and then B, and that makes sure that I don't like merge them together. I could merge them together. It's just then it's going to be, it could potentially reorder the bindings that are created, and it could be kind of weird. Now, the other thing that we could potentially do here is rather than use dict, we could use association lists, and then they are like in the order that you want. Underneath the covers, you know, it kind of depends on the platform, but if we're compiling Erlang, which we are, then it uses the map type, which doesn't necessarily preserve order. So I'm kind of like, you know, does it matter? Am I really, you know, does it really matter? Should I just merge these two bindings? I don't know if any of you have feelings on that. You know what? This is a bit too complicated. Let's see about right that we have already guaranteed by this running counter that we're threading through that they won't have conflicting bindings. So let's get rid of that. Let's pipe that dict merge bindings B, and then we'll pipe that to the fold. Okay, so this is basically the same for plus. So let's copy that. And then, and we need A and B here. And then this needs to change to plus. Okay, so this is our basic pattern here. Now let's do RCO atom. Okay, so we're gonna match on the input expression, and here's where we can use this stuff that we did. So let's just paste these in here. We know if it's an integer, and we're not going to use sum anymore. So if it's right, so this needs to be atomic expression, and here we don't have, we just create an empty dictionary, and we don't change counter, right? And same thing here. Okay, so let's add the missing patterns. This is where it's going to get interesting. All right. I think that what happens here is that once we're in here, we know that this thing needs to be an atomic expression, so we need to, right, so let is complex. Primitive is complex. So each of these needs to introduce a variable. Okay, so let's do a little function here that makes a new variable. And we'll give it the counter, which is an int, and it's going to return okay, so let's do this is dumb, but we're going to do int we don't need option anymore, I don't think. Import Gleam int toString of counter plus, let's say, new count. And we can just return this. If I can type. Okay, so, but we need to wrap that. Yeah, let's pull that back out. And we'll do elmon var name. Okay, so this is just making it easier to do this and not do it everywhere. So we're introducing a new variable. Okay, so let's forget whatever's in here. For now, I don't know that we need. Let me think about this. Okay, so new counter. So we're going to pass in the counter and increment it there. Right, fine. So what we're going to do is we're going to go, interesting, I think that this needs to return bindings as well, because we want to recurse into RCO expression. That's going to make it interesting. I don't know how we get around that. The other possibility is that we go into RCO atom. They say it was supposed to be mutually recursive. So what are the points? Obviously, we've got these are the base cases, right? In both of them. They don't give much guidance on this. They don't even have an outline of this. So I'm kind of going on my intuition. Yeah, I don't see how we don't require this to return bindings as well. I think it's that like RCO atom should produce bindings and RCO expression should consume them to wrap. Okay. What I'm concerned about is getting into the situation um, where that they warn against, where we generate too many bindings. Because in here we were assuming that this would take care of the case where right. So okay. So if yeah, okay. So if it's obviously atomic like this, we don't need to introduce any new bindings. But what we don't want to do is introduce them if oh, hold on. I think we're okay. Because if we call into this, we know we have to introduce a binding for let and for primitive operations. Let's look at the example up here. Like, we don't want to do this. So I think what's interesting here is that, like, we need to check when we're in here. Like, so when we're, the thing is, if we do this, so yeah, let's look at this program. Let me copy it down where we can see it. So if we're processing this program, we've entered here. So we get a let. And that's going to recurse into the binding expression, so 42. And we'll see that that is an int, so we'll go ahead and return that without changing the counter, not producing any new bindings. Okay, and then we'll recurse into the sub-expression, this sub-expression. And we'll see that this is a variable. It's atomic, so don't change it. Bind it to that. And then we recurse into this expression, which we see as a variable. It's atomic, return it. So I don't think that we're in the case where we will introduce any bindings unless we get to one of these primitive operations that have arguments that need to be atomic. So what I'm thinking here is that if we get into either of these, we have to create a binding, because this is part of a primitive operation that has non-atomic arguments. So the question in my mind is, are we calling RCO expression here, or are we calling RCO atom? And I think the answer is we're calling RCO expression for this and this. Okay, so let's look at this. And maybe we need a more complicated example to motivate it. The other thing we could do to unblock is to go look at the repo and see if they have some tests, some examples. Okay, well let's do this. I don't know that this is right, but probably what we can do is create some examples, and then check that our transformation works. For example, show that this transforms it into this, and that this transforms without, or this process is without being transformed. I think that's probably what we can do. Like, there's no new variables introduced, these variables aren't renamed, and so forth. Okay, so what we need to do is, so here is our new var, except we're going to do that after we transform the inner parts. So let's do binding counter B. We're going to do RCO expression of B and counter. And then we're going to do expression counter E, RCO expression of E and counter B. Okay. And then we're going to introduce a new variable. From counter E. And then what we're going to return is elmon var we're just going to return var, and we'll do dict from list just to keep it easy. Var, and here we need to reconstruct the expression. So we need elmon var let, and that's going to take feed, the variable name doesn't change, binding and expression. And then the last thing that we're going to return is this returns, sorry, new counter. Okay, what's wrong there? Oh, okay. Yeah, actually this needs to just return the name. Okay, and then we'll construct the variable up here. Right, so we need to correct that. Okay, I think this is right. And if we do this, it'll look fairly similar. So let's go ahead and do that. Let's do expression counter E, RCO expression E counter. Okay, and we'll do let var new counter, new var, counter E. And then we're going to, except that won't work. This is not, that's a prim op. So what we need to do is rewrap it. The thing is, we've covered all the other bases, so we can just do this, right? Let's call it prim expression, because then we'll know what it was. Right, okay. So now let's do the same like we did up above. So we do elmon var var of the new variable, and we'll create binding except we don't need to reconstruct the expression because this is already an elmon var expression, and then new counter. Okay, let's go ahead and make a test, and then we can hopefully move on to the explicate control. There's some bits here that I think are being made harder by the fact that they don't they didn't give a ton of guidance on this one versus what they did on some of the other ones. But let's go ahead and make a remove complex operands test.gleam. Okay, and we need lvar. I think we're going to have to do let's not do those aliases. Import langs elmon var, and then we'll be more consistent. And this is not uniqueify, but remove complex operands. Okay, and I have to remind myself. Yep. Okay, so RCO test, let's just make that. And we're gonna do the RCO no op test. This is the example that we had over here, where we don't want it to transform into that. We want it to stay basically that. It's just gonna change the structs around it. So let me copy these bits into here. And we'll copy this over as well. Okay, so let's construct this. So our initial program is going to be lvar.program. Here, need to save. What's wrong? Let's fix that. Oh, whoops. Name. What's wrong? Right. Okay, let's go there. lvar.program. And then this is going to take an expression. So lvar plus, or prim, lvar plus, and that's going to be an int 42, and lvar prim, lvar negate 10. Oops. Okay, so that's our initial program. And what we want to see, we're going to have it's going to be a let, right? And the variable is going to be temp.1. And then we're going to have the expression. You see this is a little bit more verbose so far. Okay, so now we are, let me get some line breaks in here so I can read it. So that's the outer, that's the let, and then we want to have this expression prim plus int 42 var temp.1, right? All right, what's wrong here? Oh, lmonvar. Okay, so that doesn't wrap there, and negate only takes atomic, so we don't have that extra wrapping. Okay, so now what we're going to do is p piped to remove complex operands should dot equal p2. All right. Fine. Here, let's do something dumb. Should dot equal, just so this doesn't bail on me. Okay. Okay, so that actually worked, right? That's a good sign. And in fact, it even named the variables the same thing we expect. So yay. So let's go ahead and do this one. And we'll follow a same, or the same kind of pattern. So let's make the lvar program, which is going to contain, yeah. Yes, it's just like, because we're working with functions and data here, I feel a lot more confident than I would in Python. I'm not wondering about, oh, what sneaky side effect did that thing do? Yeah, okay. So okay, so let's go ahead and make this one. So we have a let here, which is a, and this takes an expression. So in LVAR, literals are whole expressions, not atomic expressions. Okay, so that's binding A to 42. And then this one, the expression following it is B. Var up. I need to be careful because these are like named the same things, but they're from different. I wish it would actually hint to me what it should be. Okay, so here we're using A. Okay, so let A 42, let B A, B. Okay. So now we're going to make the equivalent L-monvar program. And again, like, I think that there is a potential here that we could have reused LVAR, but making it separate ensures that we didn't drop the ball somewhere, right? Like, the fact that those are atomic are encoded in the types, which is really, really nice. So it's a little bit tedious in some ways, but I think it's generally better. Okay, so what we're expecting is the parallel program, like no changes except for the types. That does mean that since let has an expression here, that means we need to do monvar. This becomes atomic, right? Okay, and then we have L-monvar let. And here's another one. So we're binding A there. And let me break this out again. The formatter will probably correct me here in a second. And this is an expression again. So B. Okay. It didn't correct it too much. So we're expecting this is turned into an atomic expression of 42, and then let has two expressions, so the expression here becomes atomic. Yep, okay. I think this looks right. And remove complex operands should equal. These tests are looking a lot the same. Let's run our test. Okay, so wait, why did we not get a new test? Why are there only 6? Oh, wait, we didn't change the number of tests. Before I had true equals true. Okay, so this one looks correct as well. We did not introduce this problem, so I think we're good there. We might need some more interesting transformations to make sure that this doesn't go haywire. But I did, I said, hey, we'd get to it. This turned out to be harder because they didn't give us as much starting point. But are you starting to get the feel like we're going through the same sorts of things each time? I'm wondering whether there's some sort of like functional pattern we can extract here. It feels very like this sort of stuff feels very monadic sequencing, like we pass that counter through, and we're getting, you know, this is like we're manually doing the chaining here. I don't know. All right, so we don't need this anymore. Let's clean that up a little bit. Okay, I'm gonna go ahead and add this, and this is section 2.5. Remove complex operands. Yep. All right. Let's look at 2.6. So they actually give us an outline here, which will help. So 2.6 is about turning L-mon-var, if we go back to here, into C-var. So C-var is that language which is a sequence of assignments and primitive operations, and then return expressions. So that's our where we're going. And let me go ahead and put this up here. Okay, I'm overriding that. Okay, so let's do explicate control. So this is explicit execution order, which is essentially a graph with gotos, is what they said. Okay, so we're going to make a new pass, explicate control. All right. So the explicate control pass compiles LVAR programs, or L-mon-var in our case, into CVAR programs that make the order of execution explicit in their syntax. For now, this amounts to flattening let constructs into a sequence of assignment statements. So they give an example. So their example is let y, let 20, x is 20, plus x, let x 22, x y. So this is the example, and they put a line break and indent there. Yeah. Okay, so they're saying okay, so that's LVAR, and the remove complex operands, they say, will transform it into, and I honestly wish that they would use the same variables, but oh, there's the uniquify, right. So okay, so that they say that the previous steps will transform that into this y, let x dot 1 20. I actually think that they'll probably have to number y as well, but let x dot 2 2. Yeah, this is not right because it would recurse in. This would be x.1. This is wrong. Honestly, the way that the racket let bindings is like, why do we have these extra parens? Why is it not just this? That bugs me as well, but here we are. Okay, and then they're saying plus x.1, x.2. And then way out here is y. Okay, let's break it up like they have it broken up. Okay. Like so. Like so. Okay. So this makes sense to me in that well, the renaming of these is not exactly right. Uniquify would also rename this, but it would probably rename this to 22. So I think that it would actually be like this, and this would be y.3 by the way that we designed our Uniquify pass. Does everybody follow that? So what they're saying this would transform into, and I'm going to have to correct it, is there be a label start, and that's x.1. We're saying x.2 is 20. x.1 is 22. And then you have, I'm going to say y.3 is equal to plus x.1, x.2, except we have them reversed. So again, this is the 3 address code and return y type of form. One thing that is interesting about the Uniquify pass that maybe we didn't talk about before is that it's going to introduce subscripts for every variable, regardless of whether that variable name has been reused in the original program. So I think that this is more accurate than what they show in the book. Okay, so it flattens let constructs into a sequence of assignments. So honestly, I think that their example here is even wrong because no. Well, I wonder. Yeah, remember that this is, oops, this is more like that. Yeah, I think it's going to assign. So when you hit, if the expression is atomic, that emits an assignment statement. If that expression is, right? Okay. Well, let's go with their outline here. So we're going to need a function. Okay, and we're going to have to import Lang's Almanvar and cvar, right? Explicate control. So this is going to take an input program, which is Almanvar program. And that's going to output a cvar C program. Okay. So we know that the contents of this program here, let's look to do. They have two functions in here, explicate tail and explicate assign. Okay. So the organization of this pass depends on the notion of tail position, to which we have alluded. Here's the definition. Okay, the following rules define when an expression is in tail position. This is sort of like, I don't know if you've ever seen operational semantics type stuff, or derivations where they have like, this is your expression, and then there'll be a horizontal bar, and then here's the transformation. This is kind of the thing they're going into, I think. Okay, in a program where E is the expression, E is in tail position. And if a let binding is in tail position, then so is E, like the trailing expression. Okay, so again, two mutually recursive functions, explicate tail and explicate assign. So explicate tail should be applied to expressions in the tail position, whereas explicate assign should be applied to expressions that occur on the right-hand side of a let. So, so in this case, we'll be calling explicate tail on the entire body of the program. This is a let. Then we'll go into the binding. We don't do anything that because that's just a name. And we call explicate assign on this. Right? And we'll call explicate tail on that. But since this is recursive, we're calling explicate assign on this. This is a let binding. So we call explicate assign on this, and we call explicate tail on this, and so forth. So mutually recursive functions. Not that different from our RCO atom and our RCO expression. Okay, so what we're going to do, we know now that this is going to take, explicate tail is going to take an input. Let's look at their, yeah. And this is going to be an Elmon var expression. And we're going to return a CVAR tail, right? Okay. What other types do we have in here? Yeah, so no. I'm sorry. Yes. Tail is the type, right? So this has to be tail. Okay. And then explicate assign is going to take an Elmon var expression. Okay. And it's going to take the variable name, give me a string, and then they have cont, and I don't know what that is yet. It's like this is the we have the sort of oh right, this is going to be a tail. So this is like what you do next. So this is going to be cvar tail. And this has to return a cvar tail, right? Because I believe that's what it is. And I think here, I'm going to get rid of this type. I don't think that we're going to use it at all. We're not going to even use it on matching. So I think what we're going to do is change this to string. And this is going to be string. That'll simplify things. I think previously I felt like we were going to need that expression. Like that is a separate type. But that's not the case. Okay. We're getting up close to time. I might go over a little bit because I feel like this we should really dig into this, and this is a really interesting transformation. Okay. Right. So they say. Okay, so they give the skeleton code, and let me stub this out, and then we'll see if what we're trying to do makes sense. And I got too much stuff on my desk here and trying to hold the book. Okay, so explicate tail does another pattern match, and like here we go again. Let's add the missing patterns. Okay. So they actually have. They smash atomic into expression. And oh no, wait, no, I'm sorry. This is Elmonvar, right? But they're matching on this as if it were Elvar, which kind of bugs me. But let's expand this out to match at least. And we'll add missing patterns. Right, okay. Okay, so this is their form for that. They also had a base case, but we're handling that with types. Okay, and then explicate assign has something similar. So okay, so what we do on the interesting thing about so explicate tail, where you have an integer, what you do is you return and if this is an int I, so you return What is the contents of that? Just an expression. So C var. The interesting thing here is I feel like our definition of C var is slightly wrong, and that you should only be able to return atomics. They look back at their definition here. They say expression, which to me seems like a mistake. You should only be able to return things that have already been evaluated, not expressions, right? Because you want to make assignments for every step. So I feel like I want to change this. So return should only be able to be an atomic. I don't know if I'm ready to be married to that. But I think that's right. Here, let's close a lot of these, and we'll reopen this and this. Not Alvar. Explicate control, and CVAR and Elmonvar. Okay, so we don't have all the extra stuff. Okay, so the problem here is it's not picking up. Here, let's Gleam clean, Gleam build. What's wrong? Return, I said, should be an atomic. Right? Why did it not pick that up? Expected type atomic got expression. Oh, I must have wrapped it incorrectly. Right, so this is just, yeah. It was right, I was wrong. Right, because I don't think that if it can actually contain an expression, unless this is something you do in a further phase, like it seems like no, you need to handle it in this phase. That seems like a bug in their definition. So I don't know. Maybe they fixed this in the version that's on GitHub. I don't know. But there's a problem here in that saying return of an expression means that you haven't flattened it into either a sequence of assignments or like 3 address operations, like binary operations with an assignment. So so I think that this has to be an atomic for return. Okay. Yeah. Yeah, this paper is well defined and includes all the implementation requirements. Yeah, we've been down this path before, folks. So we're going to do return cvar.variable v. Let's rename that. Will it rename? It's fine. Okay, so if you've got an atomic expression, that's a return. Okay. So for let, what we need to do is here's the variable, here's the let's just say binding, and say this is expression. We can use B. Okay, so for this, what we want to do is we need to call explicate a sign on the binding, right? But we call explicate tail on this first. So let's say let tail is explicate tail of E. And then what we return is explicate a sign of B is the expression, V, and then the tail is there. That's not so bad. Okay, so then for primitive operations, we need to handle those. And I think that we need to explode this. Let's see if there's a... Wish there were an easy... There's one for the Rust analyzer, but I don't know if there's one for Gleam. Right, so prim is going to be a prim op, I'm guessing again. Yeah. So for read, and then what we'll do is we will add missing patterns for the rest of these. Okay, so for read, we have so we're in tail position. I think we just return this is a problem though, because and this is maybe why they have CVAR defined with expression in the return position, because read is an expression. And I wonder if we need to generate a variable here. Okay, I don't usually do this, but I'm gonna pull open their support code. So this is the Racket one, and they have an interpreter for CVAR. Okay, interpret statement, interpret tail. Okay, so yeah, their interpret statement is assignment, and it just inserts the result of interpreting expression, and this inherits from This is the thing with having, like, we have strict types in, right? So that this interprets, it says LVAR is the parent language. So they're just kind of reusing these symbols. So if there's a prim, we don't have that luxury. Here's the LVAR interpreter, right? And there's this interprets lint. Right, so they're kind of layering this with, and here's the primitive operations, right? So yeah, we're not doing that. Okay. So do we learn anything from this is my question. It's not, it's kind of treating read not as something that you would assign to and then return. It's like jump, basically. So I don't know what to do with this yet. We'll leave that as a to-do. But let's think about these operations. Okay, I'm going to turn back to the spot we were at before. Okay, so basically this, continuation passing, or they call it accumulator passing style, is what we're doing here. So let's think about minus. This is A and B, and we know that these are atomic, right? So the question is, what do we do with those? Okay. I wonder about this. Maybe I need to back out my original assumption about this being an atomic, and this has to be an expression, because this makes more sense, right? Than the primitive operations. But what I'm not seeing is how we, because it feels like, oh, we'll have to strip off that return. And maybe that's what we do in explicate assign, is that we go when we call explicate tail, on the sub expressions in here, like so, this might have a return in it. Now, what might happen is that we keep these in there, but CVAR return, it just does like a move of whatever this is into RAX, right? Every time I hear you say Elvar, I think Elvar like Lindsay's Elvars. Yeah, I think that too. Lattice vars. Okay. Um, yeah, because I wonder if we're doing things like this, will we get issues where because we're kind of unfolding here, right? We're taking this sort of mutually recursive nested thing and turning it into a flat list of expressions. So there should be, or assignments rather. So there should be something that like slurps it out and puts it above, sort of like what we were doing in remove complex operands, where we you know, expanded the bindings and then folded out the bindings around that expression. There might be something that we need to do here. Like if there's if there are returns, because this but these are not atomic here necessarily. I guess that makes sense because you can either have but like all the contents of primop are atomic, right? So if you have an assignment, then its inputs are all atomic. So an expression can yeah, I guess that makes sense. It feels weird to say something like return read, though. Because I think that we were not supposed to have that sort of thing. Okay. Well, let's go forth and assume that this is how we'll do it. And we'll say cvar return. And this will be cvar prim right. Doesn't feel right. And I think that we're gonna, like, I'm worried about this being all returns. Obviously the let will not. We'll be doing something else there. We'll be like, this is sequence, because let me finish before we go any farther. Let me finish this. In this case, so if we have an int, we know that this needs to be this is a sequence, and this statement is assign, and v is the variable, right? Here's the integer. So if this is an assignment of this variable to this integer, we need cvar dot. The assign is an expression. Yeah. So Adam is an expression int I. And then the sequence is it's an assignment and then the continuation. So here we were creating the tail, and here's where we're adding we're adding the assignment on the front before we evaluate the rest of it. So this is kind of the unfurling of the let bindings. So let's do the same for this. It'll be like so, except this will be var variable. I had to name it something different, didn't I? Okay, so there's our assignment of atomics. But if you're assigning so let is there's the binding and the expression. I think we do something similar to what we do up here, right? With we do let tail is explicate tail expression, and then we do so this could be a tail expression. Let's rename this to B. Keep it short. So this is a tail expression as well. So then we do an assign of so this needs to be, we need to assign v1 hold on. Up here we did explicate assign on the binding. Yeah, so that's what we need to do here. So we do explicate assign, and that takes the expression and v1, and the continuation is tail. Do we just do the same thing? Interesting. I mean, that makes sense. Except that we need to we are also needing to deal with this assignment, the one that we came in here with. All right, so that evaluates this expression. So this returns a tail. We need to do this sort of assignment thing again, right? So what are we getting? The problem is this is a tail. And what we need you know what, let's pass on this for a moment because I think the assignment is going to be easier for these. And then we'll add missing patterns. Okay. So if we're assigning v the value of read, then we want a sequence. V, and then we want this, remember, has to be an expression. Right? Okay, so that's straightforward. For this one, again, we're going to do a sequence. We're going to assign V. So this is A and B. And we know that A is atomic and B is atomic. So so we're going to need a little function, convert, and this is going to be an input. We need lvar dot lmonvar dot atomic dot a, come on, atm. And we're going to produce a cvar dot atomic dot atm. Yep. I'm just going to reify this because it's a really dumb transformation, but okay, so this is going to be, let me rename this to ATM, automated teller machine, convert ATM of A and convert ATM of B. So these have to be Okay, and then sequence needs the continuation. So actually up here, this is interesting. We can collapse these two now because we don't need this. We just need convert ATM of A. Okay. So let's go ahead and do this. This is going to be very similar. As you might guess, we are getting lots of repetition here, but that's okay. Let me make sure that I've got this. Yeah, something's wrong there. So assign V to the primitive expression, cvar negate. There's that. Yeah, we need another paren there. Let's go ahead and wrap this in curly braces and then I wish it would give me more help here. Okay. So sequence, it's not complaining, but it's not reformatting. That doesn't look right. cvar assign V prim negate okay, I guess it's fine. What's wrong here? Oh, I think the problem is we are what's going on here? The problem is up here. Okay, so we have sequence. We're missing a paren there. Okay. There we go. Negate, neg. Boy, I should have named these things the same thing. Okay, and now we'll do the same, and I'll move this one up so that minus and plus are together, or maybe I'll move negate up. Yeah, that's probably better. And we do the same thing as we did there. So let's copy that and change minus to plus. Okay, so now that we have these, let's think about what this let does. And I think that we can probably fill out the rest of those in a second. But this inner let is breaking my brain. So what we want we have, let's comment this out. So we have something like let V is let V1 of B, and I'm not using their correct syntax, E expression. That's what we're trying to process here. No. Let's see. Oh, right. Expression is the let, right? So this is what we're doing here, and this is continuation. So let can be in tail position. So I think what we do, we don't bother with this. What we do is we call, let's get the tail of the inner, right? Let's see. Essentially, we want this inner let to come first. We want to assign the result of it to V, and then call the continuation. I think it's explicate assign again here. This doesn't feel quite right, but we're gonna evaluate expression to V1, and then we're gonna pass, no, B to V1, we're gonna pass E, right? So this will return a tail, and then we want to do our own continuation. Okay, so we know that this is likely to return, well, in all cases, we're returning a sequence. How do we flatten this? Is it that we do no, I think it's, so what we do is we do okay. So what we want is the result of E to flow into variable V, right? So our continuation looks like our continuation looks like cvar cvar assign. So we're going to assign v1 The problem with this explicate tail is it returns a tail. And if we're going to assign has to be an expression. So we need a match on explicate tail. But what I want to get to, and we'll figure, we'll say there's a new continuation here. we want to explicate a sign. Da, 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 da. We want to make a new continuation. B is not quite right. Maybe it is. Okay. Maybe we don't need... Okay. Because, like, what we want to do is know... Let's think about this and look at how it would be translated into our CVAR, like what we want it to look like. So we're gonna have, let's just assume this is top level, and this, remember, this cont can be any expression. Or any tail expression. So it could be a sequence of assignments, or it could be return. And we want to get... So we know that in a let, we need to evaluate the binding and then assign it to that variable. So we need something like v1 v1 is equal to whatever b is, result of b. And then we need to, v1 will be used inside the expression e. So we need something for the value of the result of evaluating this expression to go into. I'm going to put little how we're translating this, what that sort of looks like in the negative of a. So those are the things that so then the continuation comes after that. When I was first doing a project like this, and wow, it's 10 after 4. I'm going to keep going for a bit longer because I want to get my brain wrapped around this. But when I was first doing a project like this, I tried to compile to Beam bytecode. I was using Elixir, not Gleam. And when I got to this continuation passing thing, it broke my brain. Now, I kind of understand, like, you could think of it like a right-hand recursion. So if you've ever done in Erlang something that looks like do, you know, we'll call it recurse, right? And you did something like, you know, head, tail, and you did, you returned something like do the thing on H, and cons that on to recurse right, tail, and then you had a clause that was like right of the empty list, which returns the empty list. This sort of pattern, I mean, it's sort of like we're doing this, but it looks more like, but yeah, it is kind of like you're doing a cons. So you're doing this, but the other way you could do it is like continuation. Yeah, that's how I implement my while loop. Yep. It could look like continuation. You return this, right? But if you're doing you would do like this would be sort of like I guess it would be recurse continuation. This is wrong, by the way. T, you know, do something. So you're kind of putting the doing it inside out versus this where you're explicitly recursing right, and then you're performing this and consing on the front. This is like, this actually reverses the list in a sense by performing your operation. You would never do this. Like, don't do this. Use the built-in functions. But what I'm trying to get to is how does this work for our understanding of continuation passing in this context? So this would be like, if we're doing an assign, this is the assign. And this is what you would do next. But what we kind of want okay, so what we want is that, and then we want V equals E, and then we want continuation. So can we say like this is a this is something we can recurse into? That's why I'm thinking we call yeah, okay. So what we want is our new continuation is this plus this. So how do we I think we want to explicate tail on B. because you could think of it as this is a this could be its own program, right? This whatever's inside B here could be its own program. And then you're assigning so if it's return should contain an expression. Here I am back where I was just a few minutes ago. You know, or is it rather than E here? Right, so we do explicate. Maybe we can't do explicate tail there. Okay, we have to evaluate B, or we have to explode B and assign it to V1, right? And this is a tail. Let's just say B is like read, right? Then what we'll get is a sequence of assign to V1 the read. That's fine. Okay, so then what we want is, what's the contents of E? We're going to explicate tail of E. So we're going to except these are reversed. So what we want to do is, after we've evaluated B, after we've exploded B, we want to continue with what's the contents of E. Okay, so now we've got this. So this is a tail. This is this block. The problem here, oh, I see it, I think. we need to I wonder if I'm trying too hard here. Like maybe I forgot the way that you can. Yeah, maybe I'm trying too hard here, and what we need to do is do explicate tail on this entire thing, because then it'll go back up here, right? And it'll do the inner assignment, and the tail will be this. This is basically like what we were doing, we're trying to do it twice down here. So I think that what we do is let's move this clause down to the bottom, because we're taking care of all of the primitive expressions. This is a let expression, and what we're going to do is we're going to say we'll call explicate tail on this. So we're going to do, and how does that help us? This needs to come before, like the sequence of assignments need to come before our continuation. We never want to call these functions on the continuation. Continuation is always already constructed. I think this is wrong, but because this returns a tail expression, not, or this returns a tail, not an expression. Yeah, so this is the easy one, right? If it's a sequence, it's like we need to make this come before ours. Right? Which means we need to kind of like unwrap. Or we need to recurse. Yeah, it's like we need to recurse down into this tail. and then stick our assignment in. With our continuation, and then put everything else before it. And this is the like the inside out thing continuation passing style does. But I'm trying to think of how do we get there? We basically need to do explicate assign here. But we're skipping over it by going into here, right? All right. I want to continue. Like, this is probably the longest stream I've ever done. But I feel like I'm almost on the verge of getting it. So yeah, let's continue. Let's finish these out because these are very similar. This is going to be cvar minus convert. And we'll copy that. This is going to be negate. And we'll get rid of this extra argument. Or neg. Okay, and then sometimes I wish the order would come differently, but that's okay. Alphabetical or something? No, actually no. It's not. Okay, this is A and B. So the difference I'm seeing here is that, you know, these clauses are very similar to the ones below in the other function. The difference is that these are always a return. So these are like, you're at the end. And I feel like explicate assign will, I guess we need to determine if what's in tail position. And I think that expression is not in tail position. So we shouldn't treat it like tail position, right? So we kind of need, where did we put that? Let's go ahead and return this to the let. And think about it one more time. I think if we can figure this one out, then we've cracked the entire code. And I don't have to keep you know, stressing about it. So let's use their example that I wrote up above that looks like this, and we will like try to think through it one more time. Let me put a to-do on here. This is way more complicated than the thing that we were trying to do, but like we could even take this inner let, right? This should turn into Oh, interesting. So looking at this let, we need to pass it the continuation y dot 3 equals that. Interesting, right? Okay, so we kind of need to do more at the top level. We need to, like, our continuation on this let is return y dot 3, right? That's our continuation for this let. And this would be, let me break it down a little bit. So we'll do let y dot 3. That's gives us the continuation is return y dot 3, right? And I'll put semicolons just so it looks like C a little bit. So that's our continuation passed into the next. So that's there's we're gonna do explicate assign. And we're going to say y dot 3 and then whatever the contents of this is, and our continuation is return y dot 3, right? Okay, so what we need to generate is y dot 3 equals this, and then we go into that. Okay. So like what it feels like to me is that we need to is this wrong? It's interesting that we've got essentially a list, like con cells type of things. Okay, so what we want to do is this will give us like y dot 3 equals whatever y dot 3, right? So all right, I think I'm this is so brain bending that I'm running out of steam, and I think that this is a good place to stop. I need to wrap my head around it, and maybe let's do one thing before we quit. What I want to do is construct this, and then I think that this is how we do it. Maybe, I'm not sure. This order may change depending on how we structure that. I need to create what the output should look like, and then see what pieces go where, right? So The problem is a mismatch between what this returns. This is supposed to return a tail expression. And most of the time it'll return in a sequence of an assign and then whatever the tail is, right? The problem is we have an assign and an assign. Okay, so if we wanted to create this, it should look like we have an outer sequence and we're assigning x dot 2 to 20, and I'm going to keep this as simple as possible, and we have a sequence in there where we assign x dot 1 to 22, and then we have a sequence where we assign y dot 3 to prim plus x dot 2 x dot 1. Okay, that's interesting. Except I'm sorry, this is not right. I messed it up already. So it's nested, right? So we have like that, and that's another sequence, and it's assigned, and then there's a sequence, and there's an assign here, right? That's the assignment like that. There's still 3 address codes, so like this is an expression, you know, this is just int, right? They love 42 in this book, I swear. Okay. And then the tail expression here is return y.3. Okay, so this is what we want to produce. This is the kick. So obviously this and this and this come from this inner let expression. Actually, multiple inner let expressions. And that's fine. I think those are handled by explicate tail. It's just when we get to here that it's like, oh, what is this thing? So if this is like explicate tail on this expression, then what we would get is a return, prim plus, right? So we need to unpack that. And that becomes this. So it's like it needs to go, when you hit an assign, it needs to go all the way down into the binding with the continuation, right? But you need like, it's almost, we need to pass functions. I don't think it's sufficient to pass. I think the continuation needs to be a function. It needs to not be data. It needs to be a function that takes an expression and returns a tail. And this is probably like where I got off track. So what we're going to do is we're going to say this is a function that takes a CVAR expression and returns a CVAR tail. And I don't think that they are yeah, we'll need to figure that out. Okay. So for next time, we'll figure that out next time. And I hope you have a good week, and we'll see you next week. Thank you for hanging on so late, and I'll see you next time.